Today I will present my work on building an antibody-specific language model called AbLang and its use case for completing incomplete antibody sequences. This work was done under the supervision of Charlotte Dean from the Oxford Protein Informatics Group and Ian Mole from GSK. So antibodies are these Y-shaped proteins that consist of two heavy chains, seen in blue, and two light chains, seen in red. At the tip of the antibody, you have the variable region, which also contains the binding site. So this variable region is extremely variable, which basically allows antibodies to bind to any type of pathogen, which has made them extremely relevant for therapeutics. At the same time, this variability has also made them difficult to work with, as it's extremely difficult to figure out which antibody actually binds to your specific target. And because of this, a lot of tools have been, computational tools have been created to kind of like help us predict specific properties of antibodies. So the work I'm kind of like going to introduce to you is this language-specific model, which is has the purpose of helping us building these tools and help us understand the semantics of antibodies. So AbLang is an bird-inspired language model, and it's trained on the vast amount of data from the observed antibody space. The way we train AbLang is by something we call pre-training, where we train it on millions of unlabeled antibody sequences. Here we basically mask a random set of residues in the antibody sequence, and then we try and predict these masked residues. And the idea is that the model learns how to predict each residue based on the rest of the antibody sequence, and thereby sort of learn the semantics of antibodies. And this information is also encoded into this latent space, these residue encodings, which are near the end of the model. And the idea is that we can then take these residue encodings and then use them for residue-specific predictions, or by averaging across them for sequence-specific predictions. Thirdly, we can also keep our app head and then use the outputted likelihoods for amino acid specific predictions. So what I'll sort of show you now is an example for a problem where you can use AbLang, which you can use AbLang to solve. And this is a simple yet quite important problem of restoring missing residues. So if you just look at every sequence in OS, you can see that the majority of them are actually missing a big chunk of the N-terminus, as well as around 1% has at least one ambiguous residue somewhere in the sequence. And to solve this, what people usually do is either discard this data, or they will try and restore it using germlines. The problem with germlines is that you either need to know them, which is not always the case, or you'd have to predict them, which can be a little bit problematic. So an alternative would be to use a language model such as AbLang, where you basically throw in your sequence with your missing residue, and then you pick the likelihood for the amino acid at that position. You pick the amino acid with the highest likelihood at that position to fill in with. And this is something that has turned out to work quite well. So as you see here, where we compare AbLang with the germline method, as well as the current state-of-the-art general protein language model ISMB at restoring missing residues. So if we just look at first how they work at restoring up to 30 missing residues from the N-terminus, we can see how the general language model is struggling a lot, which is also expected. And while AbLang and the germlines are doing comparably well. And if we look at just restoring a random set of 1 to 10 missing residues, we can see how AbLang is doing better. So this is really nice, but there is one thing to note. When it comes to restoring missing residues from the N-terminus, we usually don't actually know how many residues we're missing, which is something we assume with these three methods. So how do we solve the problem of figuring out the correct length to restore? So we found out that with AbLang, we can use the predicted likelihood of the first residue to determine the full length of the antibody sequence. So what you can see here is essentially by using this approach, how well is AbLang able to correctly predict the number of residues to restore compared to a standard approach of using an antibody sequence numbering method such as anarchy. And we can see that AbLang is doing comparably or better, as well as we can also see that sometimes if we restore once with anarchy and then AbLang and then restore again like a second time with AbLang, we actually have better performances or improved in performance. And this is especially seen on longer missing regions of heavy chains. So all in all, we have shown that it's possible to train a antibody-specific language model because of the vast amount of data that is available in OS, as well as we have shown how AbLang can restore residues better than the current baseline, the germline baseline, as well as a general protein language model. And this also demonstrates why it makes sense to train a antibody-specific language model for antibody-specific problems as well. So I hope you like this talk, and if you have any questions, please come and visit me at my postdoc. Thank you.